Okay.
Fantastic.
Good. Yeah.
I think you can click the height. It is there. You see, one screen is there. You just put height, then that part will be.
Yes.
That small bar will go away. Yeah.
That will be
Right.
Yeah. Now I think we are good with this presentation.
Should we start?
Let's just wait for two more minutes because generally people join in 4:05. 4:05 we have a full house. So yeah.
Yes, you were saying something. We were doing this in the middle.
No, what I was saying, we also had Dr. Shukanto Roy. I think you know.
Okay, good, great.
Yeah, we also had him here in this forum. I think 1 year back during the pandemic time.
Oh, then hopefully all this is largely familiar. What I'm going to say.
No, not necessarily, not necessarily. But not that everyone was there during that time.
Okay.
Many young people have joined recently in our group, so I think it will be very good.
Okay.
Welcome, Chetty sir. Welcome, Dilip da.
Hello. Hello, everybody.
Oh.
Hello.
I think we can start now, and more people will join soon, I'm sure. So, good afternoon, everyone. It's my pleasure to introduce today's speaker to you. We have Dr. Kusumita Arora this afternoon. Dr. Arora is a geophysicist working in CSIR NGRI. She is a principal scientist there, and she has been working there for last 20 years. She had done her graduation and post-graduation from IIT Kharagpur, and then PhD from Osmania University in Hyderabad. And over the last 2 decades, she has pursued the application of potential field methods to investigate the structure and processes of the Earth. She is leading the study of the geomagnetic field in NGRI. She has long interest in structure and deformation. She has studied surface features from terrain models derived from airborne radar data and shallow subsurface structural features based on borehole acoustic televiewer data. She has also conducted laboratory experiments on deformation. I did not know that, Dr. Arora, on different rock samples under various stress conditions. So with this brief introduction, may I invite Dr. Arora to speak on structural fabric of Koyna-Warna seismic zone from terrain mapping and borehole observations. So the floor is yours, Dr. Arora.
Thank you so much, Dr. Malik. The basis of this study began with seismicity, which was or is or continues to be debated. The role of reservoir, particularly the Koyna reservoir, in triggering the seismicity in that area. And that seismicity has been continuing for the last 6 decades now, and a lot of studies have been done by NGRI on this. Most of which, or I should say 90% of which, is based on seismological studies. We have a strong seismological network there for many decades. So, in order to understand the causes of the seismicity, the idea was to sort of use this location as an in situ earthquake physics or earthquake mechanics laboratory, which might have been something Dr. Sukanta Rai would have talked in much larger detail. But I'll just come to the beginning because this study started in 2012. And the idea was that on the surface, this is the basalt covered Deccan Trap area. And the seismic zone sits right east to the Western Ghat escarpment at average altitudes of 1100 meter. So there is more than 1 kilometer of basalt here. The understanding is that in this basalt cover, we do not see any clear structural fabrics. Ground magnetic studies had been attempted many decades earlier. And because it's all basalt, the magnetic anomalies are very noisy. So there were no major conclusions on the structural details in this area. So, yeah. So I'll just talk of this location and the geophysical information in a nutshell. So what we got from what we know about the regional fabric and lineament pattern in the area, why we went to airborne LiDAR, and the lineaments we got from it, and try to correlate them with the fracture patterns we observed from boreholes. And finally, I'll talk of 3 sub-regions, what emerges of the seismicity pattern within this small area, and they seem to be linked to the surface and subsurface structural patterns. How does it? Oops. Yeah. So this is the location. This is the Deccan Plateau. The Western Ghat escarpment is right here. And this is the Konkan Plain on the side, to the west, the Arabian Sea. And we see that largely we see the Koyna Reservoir itself is strong as north-south and aligns along the Western Ghat escarpment. There are many north-south features to the west also. And there seems to be also a strong northwest-southeast trend here, which is also followed by some of the larger rivers. There is one major ridge here, which is also northwest-southeast. This is from the regional terrain map, which is available from a compilation of Cartosat and other data, SRTM, and all these combined gives us the look of the entire region. And this black outline is the area on which we flew airborne LiDAR. I'll come to that in a while. Overall, from 2005 to 2018, magnitude 2 and above, all the earthquakes are plotted here. So this is the Koyna Reservoir. So the earthquakes are mostly confined to the south of the Koyna Reservoir and mostly south of the Koyna River, where the Koyna River takes a bend. It comes out from the reservoir and turns to the east. And here is the seismic zone. And then there are further seismic epicenters along the Warna Reservoir and also further to the south. So a lot of studies on from all the borehole measurements. We have about 32 broadband stations and 8 borehole stations now. And I'll just give a summary in that at 0 kilometer, this is what VP looks like. And as we go deeper in the depth slices at 2.5, we see the decrease in the velocities here. And this is again the Koyna River for reference, and this is the Warna Reservoir, and the Warna River for reference. This is the Western Ghat. As we go to the depths of 5 kilometer, the higher velocities fade, and we come more and more towards the lower velocities we see here. So this is mostly 6 kilometer per second. And so at 10 kilometer and at 12 kilometer, they are more like 8 kilometers per second. And VPVS ratios are also similarly, they even out when we go to about 12.5 kilometers, and the VPVS ratios have more contrasts when we are, of course, near surface, and from 2.5 to about 7.5 kilometer. And interestingly, we know from the earthquakes, even the first earthquake, which was the largest one, 6.3, and later that most of the earthquakes have focal depths of around 8 kilometer and shallower, 8 kilometer to 4 or 3.5 kilometer. So they kind of have some correlation with the velocity structure. The seismology has also tried to look at the spatial variation in anisotropy and found that beneath the Koyna region, which is here in this area, we have north-south, north-northwest, south-southeast, and north-northeast, south-southwest directions, whereas in the Warna region, it's mostly northwest-southeast, and some east-west components also. Not a significant variation in anisotropy is observed with depth. And PNT axis orientations are derived from the focal mechanism solutions. And the compressive stress, principal compressive stress is sigma 1 in red. Here that appears to be north-northeast, south-south, north-south mostly. And tensile in blue is mostly in the east-west direction. And I haven't added more details of the earthquakes themselves, but here we have mostly strike-slip earthquakes. And in the Warna region, we have mostly normal earthquakes with some strike-slip components. GPS, we have, I think, nearly about 15 years of data now from 5 GPS stations. And these GPS also, these are the stations here, 1, 2, 3, 4, 5. These are the 5, and this one is the new 6th one at Nari. And it shows a very small 0.1 to 0.7 millimeter per year deformation in northeast southwest direction in this region, and even a smaller magnitude arrows in the Warna region. In Kundi, which is west of the Western Ghat, there it's east-west and slightly more than in Warna. So I'm not sure how this differential is getting accommodated. So with this idea that that there was not much structural information on the surface, and it was decided that we need to look at it. So there was a lot of debate as to what would be the best way to look at this, and we did look at imagery data, and which may be purchased from NRSC, and because of the large slopes of the terrain and the vegetation cover, it was decided that we would go for an active source, which would be a LiDAR, and we'd use a fixed wing aircraft to acquire this data. I think now LiDAR is very familiar technique. It has become over the last years, and it has many applications in urban mapping, in city areas, in land use, in clouds, in forest cover, and things like that, even in mining also. So here we took a very small fixed wing aircraft, and we flew at around 600 to 700 meter AGL, draping the topography as far as possible. We covered an area only over the plateau. We could not go to the west of the plateau, where the drop was too sharp for the aircraft to accommodate. And then the aircraft has a laser beam transmitter and receiver. So it transmits and receives in a swathe, and collects the first returns, the second returns, up to 4 returns of or reflections of the transmitted laser. It can record. And we were inside, we were in the craft, we were recording this data and checking for it. And it took about 30 days of data acquisition with a lot of overlaps. So once all the data is acquired, what we have are a raw point cloud, and the point cloud is colored according to the elevation of the return. So this looks like a raw point cloud of one swathe of the LiDAR data acquisition. And when we try to process it, we see the difference in the altitudes much more clearly. And I was, at that time, I was very new to this, and I was very excited to see that you can see the power lines as well as individual trees, the power pillar. In fact, many places we have imaged the windmills as well, which are there all along the Western Ghats, and then some of the ground data. We also took photo imagery, orthophotos of the area we were flying over, and we used these photographs to classify the point clouds as power lines and pylons, vegetation points, ground points, and things like that. So once all the classification is done and verified, then we use only the ground points to generate the surface using different methods of triangulation. And I will not go into the details how we actually try to calculate the triangulations. They are standard techniques, and this is a 1 kilometer by 1 kilometer 8 square kilometer area. And here we see the surface emerging, and the small dots, they are all the vegetations on the surface. And then we have to clear these are very low level vegetations and have to be cleared again with another round of computation. And here we get the first image of what we think do not contain any effects of the vegetation. And then we have to recompute using more detailed computation of each of the tiles, and more and more details of the terrain emerges. So once we compile all this in, we have the terrain in this much detail, but at a one look, this is what it looks like. The terrain model over the entire area. This is the southern end of the Koyna Reservoir. And here it turns, here it's slightly northeast southwest. The Koyna River emerges here, takes 2 bends and flows east. This is the Warna Reservoir, and the Warna River emerges from it and flows northwest southeast. This is the Western Ghat escarpment. So we use this terrain model, and we used it from many different with many different angles of illumination, and we used length persistency and curvature features. We first identified some of the features visually, and then computed their curvature and computed their consistency to emerge with sets of lineaments which were crossing the area of this LiDAR covered terrain. From some of them, many of them were north-south, and there seemed to be parallel sets of lineaments here, and more north-south in the apparent on the surface near the northern part, which is near the Koyna Reservoir. Two very prominent northwest-southeast features, and some northwest-southeast features, and they were both of them ridges actually, and the Koyna Reservoir was in a trough between these two ridges, and there were also northeast-southwest lineaments. On the surface, there did not seem to be very prominent east-west features, which would have mimicked the flow of the Koyna River, but the computations did not show very clear persistent curvatures, except the river itself or the river channel. Other than this, we again try to compute the minor lineaments, which will be less than 1 kilometer actually in persistence, and they mostly coincided with the very small channels of river. For example, these kind of channels all came up as minor lineaments in this area, and we also use them to make the drainage pattern of the area and see how the seismicity goes along with the drainage pattern. And and later further from this, we map the basins in this area. Some of them seem to be very small, and some of them are larger and more persistent in their features. And we drew the fifth order drainages on this. All the major tributaries, which are even there for 6 months of the year, are reflected in this map. We have used the standard basin asymmetry factors, elongation ratio, hypsometric integral, stream length gradient index, and valley width to height ratios to demarcate the index of relative active tectonics in most of them. But the very smaller ones, it was very difficult to make these computations. And we have again superposed the seismicity on these zones of active tectonics, the red ones being the most active, the yellows are moderate, and the greens are less active. And we see here that in the Koyna region, the northern part of our study area, the seismicity falls along the active zone mostly. Here there are significant seismicity which we could not calculate, partly because the LiDAR does not give does not give a terrain model in the water regions, and the Warna Reservoir is here, so we don't have terrain model data here. Here also the active region as calculated from our factors were also coincide with the zone of most intense seismicity. Some of these active regions here, of course, do not coincide with any epicentral zones, at least at the moment. So after that, we tried to now look at the third dimension, the Z. So far, we had been looking at the surface features only, and we had aeromagnetic anomalies which were flown. These aeromagnetic airborne magnetic survey was made much earlier, before 2004 actually. The results were published in 2004, and they were flown at three different heights. One was 1220 meter, one was 1524 meter, and one was 2100 meter. So they give a very good example of how the basalts affect the magnetic measurements, and how when we increase the height, we get information of the greater depths in the below the surface. So this is the map of this entire survey. At 1220 meter, we see a lot of anomalies here, and it seems to be a mesh. So there is a fair influence of the magnetic properties of the basalts, which vary a lot. The susceptibility has a lot of variations in these measurements. After this, we also had a look at the 1524 meter anomalies, and they seem to be dominated by east-west features here. Many of them are east-west features, and not a lot seems to be coinciding with these patterns of the earthquakes here. And there are some northwest southeast features. Even on this is the Deccan Plateau, and this part is the Konkan Plain. And here there are some northwest southeast features, and here there are some, but mostly it is dominated by east-west feature. So these are deeper than the anomalies that we saw on the earlier map, which was at 1220 meter. And next we have the 2134 meter, which reflects information from, say, about 5.56 kilometer to about 8 kilometer, based on simple spectral analysis. And here also we continue to see the dominance of the east-west features here, right across the escarpment. So the escarpment is somewhere here, and these features move right from the Konkan into the plateau. Somewhere here we see more north-south or northwest-southeast features, and one is quite prominent from here to around here, and part of this seem to coincide with the distribution of the earthquake patterns here. And so what we did afterwards was, let me see, we tried to calculate the tilt derivatives of the anomalies. The earlier one were the anomalies themselves. Then we calculated the analytical signal, and then we calculated the tilt derivatives. This is from the 1220 meter tilt derivative, and this is from the 1220 meter we have left out because it's too noisy. And this is the 1524 meter, 1.5 kilometer, and this is 2 kilometer flight height. So here the number of anomalies in the tilt derivative map are much less. We see a prominent, again, east-west slightly curved anomaly here, and one northwest southeast here. Here we see more of north-south features, which are not reflected here. So we have to speculate, or we have to infer that these are shallower features. There are more northeast features here, and they coincide closely with the escarpment itself. There are some smaller north-south features here also. So these are what we get in the subsurface from magnetic data. And the lineaments which we have inferred from the LiDAR terrain model, we have superposed on these trends. And here we see that some of them coincide well and others do not. For example, these east-west seem to be here on the surface, whereas there is an east-west here in the subsurface, which coincides, which in fact becomes more prominent or as we go deeper into the basement, around 5 kilometer and more. So this was the first attempt to visually correlate the maps of the surface and subsurface features. We have done it the other way around also. We tried to superpose the anomaly maps back onto the terrain model and try to check how the trends inferred from the magnetic lineaments match with the surface terrain model. and whether we see continuation of them here. Some of them, if we go even out of this area, we see them as continuations in the north-south direction, and some east-west features which are in the map are seen as roughly east-west sections of the flowing rivers. We have done it for all the three maps. This is 1524, and here the northwest northwest southeast is becoming more prominent, and it also coincides with the map with the features that we can see on the surface. And here, these deeper features are not seen on the surface at all, except that here the Koyna River is flowing, but here we do not see anything on the surface. And here, of course, this coincides with the northwest southeast ridge running beside the Warna Reservoir. So, in summary, so these are the lineaments on the surface, or structural trends from the surface, from the terrain model, and these prominent ones are the ones we get from the tilt derivatives from the depths. These are it's difficult to pinpoint one single depth, but they lie between 3 to 8 kilometers in depth. So now we also want to check them with real data. Of course, we don't have real data from beyond the boreholes, and these boreholes are all about 1.5 kilometer in depth, and there are actually 9 boreholes here. One which is just south of the Koyna Reservoir, 2 more on the plateau itself, Y2, 1, 2, 3, 4 on the plateau. This one is very near the Western Ghat, and then 4 on the Konkan Plains also. And the seismicity map is again, epicentral distribution is again plotted here. We have been able to have televiewer data from 4 boreholes only. We do not have televiewer data from the rest of them. So we have concentrated on these 4 boreholes, 2 from the Deccan Plateau and 2 from the west of the Western Ghats, which are about 600 meter lower in altitude. And we have done a full lithological mapping and 1:1 meter, at 1 meter resolution. So we will discuss the results or observations from these 4 boreholes. These are some examples or some photographs of the cores which were retrieved at one of these boreholes. This is this one. This borehole turned out to be the most fractured borehole that we have, and the core recovery was also less than the others. And these are basalts, amygdaloidal vertical fractures in the basalt, thin vertical fractures, highly fractured zone in hard and massive basalts. So just some photographs to show the kind of material that was encountered while drilling. Some silicon side or silicon fiber features were observed in the basalts. We have not observed silicon fibers in the basement formations or below the basalts, except for in one borehole so far. I don't know whether we should look again more closely. So these are 900 and 930 meter depth still basalts, and 1071 to 1081 again hard and massive basalts here. So I did not include any photographs of the basement here, but we have some. We have about 1100 meter of basalts through which the boreholes were drilled, and then we have about 400 to 500 meter of the basement rocks, which are diorites, granites, granodiorites, saprolites, things like that. So here, this is a first view of a result from an acoustic televiewer log. This is very similar to sonography that is done for in the medical region. So we have this whole borehole filled with water, and the sensor goes through them, and it actually the features which come out like this, the sinusoids here, and the dark ones are where there was no reflection back from the wall of the borehole, and the bright wherever there was a reflection from the back sides of the borehole, we have a clean sinusoidal feature, and these features are reconstructed back into the planes of these fractures. Each of these blacks are deeper fracture, dark blues are the deeper fractures through which the energy escaped. And here, when we don't have fractures, or we have a very thin fracture, but there is no actual break in the wall of the borehole, there we get a clean image of this plane. So when we look at these planes, they look like this, and these dark regions are where we do not have any reflection back from the borehole walls. So the two colors, these are natural fractures, and these are drilling-induced fractures. How we identify them? We have some standard descriptions of what are natural and what are drilling-induced fractures, and we wrote a small algorithm to scan through all the 4 kilometer of data. We have some data gaps, of course, it's not fully 4 kilometer, to identify which are the drilling-induced and which are the natural fractures. For example, the natural fractures have stronger intensities compared to the drilling-induced fractures. And then we have joints and veins. These are the 4 classifications of features we observe in acoustic televiewer data. And in joints, we have less continuity. The morphology of the features are different. So in veins also. And we also see them as many small subparallel features when we reconstruct them, reconstruct the surfaces. So whereas the original idea was to, in fact, study the joints and veins, but we have not yet come to that. But we have used all the identified natural fractures and the drilling-induced fractures, both in the basalts and in the granites. And the strikes in the basalts and granites change. The dip angles also change. The strike directions of drilling-induced fractures are, on the whole, similar to the natural fractures, but sometimes the dip angles are more scattered, as in this one. These are different in different boreholes, and they also depend a lot on the lithology. For example, if you have a very compact material through which drilling is happening, then drilling-induced fractures have a very coherent strike direction and dip angle. So this is what has been done for for 5 boreholes, one of which we do not have any data in the basalt region, but we have from the basement. For 5 boreholes, we have the total fracture pattern from the acoustic televiewer data. So we use this to construct the first look of all the region as from the shallow surface. Here, this is this borehole, and this part above this white line is the basalt section, and this is the basement below the basalt. Here, this one is the one where we do not have any data in the basalt. Here again, we have data both in the basalt and in the basement. Here, the basement depths are higher, and also in this one, this is the basalt, and this is the basement, more or less similar in depth. In this borehole, we see that there is a lot of low dip fractures in this region, which is quite different from the fractures in the basalt. So whether this indicates some major discontinuity in the way the fracture patterns have persisted between from the basalts to the basement. I mean, we need more data to work on this, because from the magnetic data we are not able to have information of this resolution. This is the overall look of one borehole, in which we look at the strike, dip azimuth and dip angle of natural fractures, of induced fractures of joints and veins. And in the basement, you see the strike direction has changed a lot. Dip azimuth and dip angle has also changed totally in this borehole, which in fact is this one here. And we do not have any, we could not retrieve any joint information in the basement. Probably there are none, but we do have some veins, and they show a lot of scatter. So when we look, we have compiled this for all the boreholes that we have. And for one borehole, the basalt information is not retrievable. For the borehole where I showed that there was a lot of fractures, we could not, the basement rocks were totally fractured. There was no ATV data which could be retrieved, so we do not have information here. And otherwise, this is what the fracture information in the basalt and basement looks like. So we see that consistently there is more scatter in the basalts, because they, I mean, that's the because of the lithology itself. And as far as dip angles are concerned, we also see a fair amount of scatter both in the basalts and in the basement. Whereas these two are the boreholes which are west of the Western Ghats and in the Konkan. So these have more scatter in the dip angles. Here on the Deccan Plateau, the dip angles have less scatter. In the natural induced fractures vary between 45 to about 60, whereas the drilling induced we found were mostly very high angle fractures. The strikes, the strikes are here. The strikes are mostly north-south, or north-south. In the basalt also, it was mostly north-south. In the borehole, which is very close to the escarpment, which is, sorry, it's not here. It was this one. We see that, we see that it's absolutely aligned along the escarpment itself. So we see that the induced fractures are relatively scattered in these two boreholes, and less so in the boreholes on the Deccan Plateau, and the natural fractures also follow a similar trend. In the basement, the induced fractures are north-south here. In this basalt, in this borehole, which coincides very closely with the dominant trend of surface lineaments which run through this area. It is northwest-southeast in this borehole, which also aligns very closely to the lineament passing through this region. Northwest-southeast and north-south in this one, the borehole 6, and north-south, north-northeast, south-southwest in borehole 8 here, this one. And natural fractures also follow a similar trend with greater scatter. So when we take an averaged picture, so here we see the Okay. Here we see that this borehole, which was north-south on the surface and slightly northeast southwest in the basement, lies here. And here we have the P wave velocities are higher in the Deccan in the Deccan Trap region, west of the Western Ghats in the Konkan, and slightly lower on the plateau. This may be an effect of the accumulated basalts here and the loss of seismic energy in the basalts. Okay, when we look at the drilling induced and natural fracture directions, they are like this. This is in the basalts, and here this is in the basement section. So they change quite a bit in this borehole, and also in this borehole, which are very close to the northern part of the Warna Reservoir. They are the same in this borehole, where the continuity of the fractures in the basement, but here it is true that the information from the basement is less, because a lot of rocks were, ATV data was very little because the rocks were fractured. And here also in Okalu we have dominant north-south direction drilling induced, whereas the natural fractures were more northwest-southeast. So based on this, a pattern emerges that even within this small area of 40 kilometer width by 60 kilometer length, we seem to have three different regions. And one is in the northern section. This may be a little bit difficult to identify on the map, but I will just point out that, 1 minute. Yeah, this is the Koyna River. So this tile is just south of the Koyna River. And this is the northernmost strand of the Warna Reservoir. So this is a bit of a central section, and this is the main Warna Reservoir. So this is the southernmost section. And seismicity pattern is the small black dots. It may not be very visible here, but these black dots are translated into all the magnetic anomaly maps in each of these locations. And we can see how, when we look at it separately, we see that the north-south and northeast-southwest dominate in this region. And here it already starts to become northwest-southeast at the larger depths. And north-south high-low pairs nearly parallel to the Western Ghat escarpment. Here we see in the southernmost section, we again see a dominance of north-south features, except in the section which represents the larger depth, where we see a significant northwest-southeast feature. So this idea that the structural patterns of the three regions could be correlated to some differences in the earthquake occurrence patterns as well was also tried out. And we had identified this region as region A and region B and region C. And we see that is based on the maps we had made here, and also on the clusters of seismicity and their alignments from the epicentral distributions. So when we look at, so A is the northern section, B the intermediate, it's most strongly, here the seismicity is aligned along the northwest-southeast feature. And here in the southernmost section C, it is, here the epicentral cluster is sort of aligned north-south, the earthquakes are elongated in nature, and there was a more recent publication where they have shown that micro earthquakes are migrating further to the south a little bit more. I think they've come right up to here, but I have not been able to use that data for newer maps yet. So here the focal mechanisms show a northwest southeast normal faulting, but the uh, alignment of the epicenters are north south. So we just have tried to examine whether this is just an artifact of looking, or whether this can be verified with any other parameters, and we tried to look at the temporal variations of the earthquakes. I'll come into that in a minute. Here in this sector, which is sector A, these are the magnitude patterns, and we have, of course, in all of them, magnitude 2 to 2.4, 2.5 to 3.3, and then 3.4 to 5.1. So magnitude 2 is always the maximum, whichever section we take. But the number of small magnitude earthquakes are much larger in the section C, which is aligned north-south and lies south of the Koyna Reservoir. Now, focal depths, we see 0 to 3, 3.1 to 5, 5 to 9. Here, the largest in section A, the largest number of focal depths are between 5.1 to 9. In the central region, the focal depths are kind of all the same. And in the southern section, the largest number of earthquakes are very shallow, and then there are a few earthquakes which are 5.1 to 9. So definitely the pattern of the focal depths of the earthquakes which occur in each of the region are different, and they coincide very well with the anomalies that we saw on the magnetic maps. Now, we also tried to look at the seasonal pattern of the earthquakes, because the earthquakes have been studied always with respect to reservoir triggering. So when the reservoir is at the idea is that just after the monsoon, when the reservoir is full, so we get the largest number and largest magnitude earthquakes around August, September, and and after October, November, and December, we do not have that many earthquakes. But when the dry season is fully there, then again we have some more number of earthquakes which are occurring. So we tried to have a look at this, and we have used data again from 2005 to 2018, and we see that in the northern sector, March to June, July to October, and November to February all seem to have very similar number of earthquakes. This pattern is again the most prominent in the southernmost section, where November to February, the number of earthquakes which occur in this region are highest, compared to very similar number of earthquakes which in fact occur even after the monsoon period. So when we really examine the data, we see that there is more of a trend of a difference in trend when we look at each of these regions. Now we have tried to look at this magnitude pattern over the years. And here also we see that the change in magnitude, 1:2 to 2.4, like we did in this figure, 2.5 to 3.3, 3.4 to 5.1. And here we see again from 2005, 6, and right to 2018. And there is a slight increase in 2008. I mean, there was so much information here. I removed the rainfall map. but rainfall data over this region. But this does have a pattern which is very similar to the rainfall pattern, which shows uh, spikes in few years but have remained the same throughout. On the other hand, here in the central section in 2006 and 2018, we have a relatively larger number of earthquakes which have occurred, 2008 and 9 also. Again, the largest number being the smaller magnitude earthquakes. And in the last section, again, we see that the large number of earthquakes happened from 2005 to 2010, and now they are almost gone. And the large magnitude earthquakes, we don't see them at all. 3.4 and above, there are no earthquakes of 3.4 above 2014 onward in the southern section. All are, there are large number of earthquakes, but all of them are small and small in magnitude and very shallow in focal depth. So I think I would like to conclude here and say that using this high resolution terrain model, we revealed 3 sets of large major lineaments, and each of set was found to have good correlation with edges detected from tilt derivatives of magnetic anomalies. And based on these lineaments and the subregions of seismicity were identified, and then we have and they correspond to distinct subsurface and subsurface configurations. And they also the occurrence pattern of these earthquakes also seem to have they are different, and the differences are also corresponding to what we see on the surface and the subsurface. So how to quantify, how to model them, these in terms of the earthquake focal mechanisms, as well as what kind of forces may be occurring in them. That is something seismologists are working on. But we on our side continue to study these borehole breakouts in all the 4 boreholes that we have. Unfortunately, there's all these boreholes lie in the region B and C of the 3 regions identified, and none of the boreholes in region A have ATV data. But we would like to find out from the study of the or modeling of the borehole breakouts whether we can identify the differences in forces which may be acting at least in the shallow subsurface. Thank you very much.
Thank you very much, Dr. Arora, for a very detailed and informative talk.
Yeah.
So now we open the floor for question. Please raise your hand, then and you can interact with Dr. Arora.
Should I stop the presenting or continue?
I will suggest to keep it on if someone has a question from the slides itself.
Okay, fine.
Yeah. Any question? So while people warm up, Dr. Arora, I have 1 or 2 questions actually. So the drilling-induced tensile fractures that you talked about, they like your borehole breakout from the borehole breakout, you can calculate the direction of recent stress. Mm-hmm. Similarly, from the drilling-induced tensile fractures, also you can calculate recent stresses. They are typically parallel to the recent maximum horizontal stress. Yes. So as I see, your data is varying from one borehole to the other. So do you expect the local stress orientation to vary a lot in this region?
Yeah, I mean, we have not done that computation yet, but it seems to be it seems to point in that direction, even if we talk only of the variations that are being calculated from the small magnitude earthquakes, like seismological computations. So far, the initial result I showed from seismology were based on 4.5 and above. Mostly, the 2 magnitude earthquakes were not included because they're too numerous in number. But now, one study is being done where some 11,000 small magnitude earthquakes are also included to try to see the variations of these stresses in this very small region. And they seem to vary a lot in the region between, say, 2 to 5 kilometer depth.
Okay. And the earthquakes that we observe here, are they like mostly due to the reactivation of existing structural features, or new faults are being generated for the majority of the earthquakes? What is your opinion?
I don't know for sure, but the idea is that there is a combination of both, because that's that's another aspect of study also that we are supposed to do. What are the reactivated features, and what are features which are newly made, or what features were healed. And so from the locations where earthquakes are occurring again and again, there we have to do studies of this nature. Unfortunately, these studies we cannot really do on the basalts, and to get to the basement you have to have so many boreholes. But the idea is that the large features, north south and northwest southeast, are definitely reactivated features, but we're not very sure of the northeast southwest features. They could be probably new ones, because we don't see their continuity in the depths.
Oh, okay, thank you very much. Any more questions from the audience? Yes, yes, Professor Bose, please go ahead.
Thank you, Jyotirmoy. At the outset, I must thank Dr. Kusumita Arora for giving a very detailed talk by illustrating different techniques that she used in this study. And it's really is very good, and it's quite understandable that you should look into different corner to obtain a result and to decide upon the things what is happening there. I have just one query, Dr. Kusumita. You said that in the section A, you have a strike slip fault mostly, and towards C, you have a normal fault.
Yes.
So, do you have any reason for these differences? Because if I look at the area, I don't see that the area is very far apart. They're very close by. How come you could change the stress axis there? Do you have any explanation for this?
No, actually, but I don't know how to explain it. But the earthquakes here are strike slip, mostly right lateral,
Okay.
and the larger magnitudes and larger depth earthquakes are also in this region, and that's why we think that they are deeper in the focal depths are also larger, approximately 5 on an average, and they they I think we agree that they are along of fault which is getting reactivated again and again. And what has been mapped from seismology, they call it a Donachi-Wada fault here. and they have mapped it right from south of the Koyna Reservoir, right up to say here.
Okay.
From here. This northwest southeast feature is also very prominent, and it goes right across the Konkan. And we see them very clearly in the borehole data, both one borehole which is here in fact, and one on the boreholes in the Konkan. But there is no strike slip component here. We think that there is probably some intersection of a northwest southeast regional feature, which then intersects the north south feature here, or north northeast southwest feature here, and then this becomes, and this feature is very rigid. So the earthquakes here are much shallower. The deeper earthquakes do not exist here. There is nothing below even 4 kilometers. There is no even 5 kilometer focal depth earthquake here. They are small in magnitude, shallow, and they're mostly normal with a small strike slip component.
But you also have a shallow earthquake in the section A as well, right?
Yes, we do, but much fewer in number. The large number of shallow earthquakes happen here.
Okay. So it's good that you have characterized different types of earthquake with respect to different area. So now people are there to find it out the reason for this.
Yes.
Okay.
That is why we had initiated some laboratory results, laboratory simulations, to see whether, even keeping aside ideas of how to upscale, but even if we can mimic some of this in the laboratory. We have made some experiments, but we have not yet got to the stage where we can show the transition from strike slip to dip slip. So hopefully we will get there.
What is the average maximum compressive stress directions? I think what I mean, from the borehole breakout, you have determined the maximum compressive direction, right?
Yes, we have determined it. Again, here they are. So these three borehole breakouts that I'm showing, so they are mostly northeast, southwest, because the breakouts are northwest, southeast.
Yeah. Okay. Thank you very much. Maybe many more queries will be there. Thank you.
Any more questions? Maybe Professor Mandal or Professor Saha or Professor Mukhopadhyay or anyone from the audience. Yeah, Anumitra Shikdar, please go ahead.
Yeah, hello, ma'am. I'm a PhD student. So I just wanted to know, like, in one slide, you have shown like there are two boreholes, and the VP dropped, but the VS didn't. So it is understandable that the bulk modulus dropped, but the shear modulus didn't change. So what kind of change can?
Is this the one you're talking about?
No, the other one. I mean, where you are showing that VP and VS. With the borehole, there are 4 locations and...
Okay. Right, I got it. Yeah, these are results from our sonic logs, actually. We have the full set of logs. Yes, here. Is
this one.
About? Yeah.
I'm talking about Khadi Kolvam and some...
Fansavle, yes.
Fansavle, yeah.
Yes.
So what kind of change can... induce this kind of phenomena where the S remain constant and the P dropped?
Actually, the P is higher in the basalts in the Konkan, and also in the basement. Both of this compared to the velocities in the on the plateau, the velocities, the P wave velocities are higher. S wave velocities are also higher. Both are higher. And I think the explanation is the effect of the thickness, 1 kilometer or 1.23 kilometer thickness of the basalt themselves, because the basalts, and unfortunately here we don't have the VPVS velocities, but the basalts will absorb a lot of or dissipate a lot of seismic energy, and so the sonic waves, sonic logs show lesser velocities here, both in P and in S actually. The S here is also slightly higher. And in the basement, both the P and the S is much higher. Does that answer your question?
No, ma'am. I was asking about the Fansaule and the Khadi Kolgam. So here the SF velocity is 2149, and here it is 2146.
Same.
But yeah, it's same. But the P wave velocity dropped. Like for Fansaule it's 4603 and 4215. So that's now what kind of change in the rock, what kind of physical change may induce this pattern?
I think it's again due to the fractures rather than any change in lithology, because this Khadikolvan location, I can show you also. This is at the intersection of three lineaments. And this has a lot of, this was the borehole in which we could not recover large sections of the basement rocks because they are totally crushed. And we also see myelinization, and so this area was is a deformed part, and it's because of that I think the velocity is 4.2 here, whereas the P wave velocity is 4.6 in Fansavle, which is compact material. There is not much deformation happening there.
Okay, ma'am. Thank you.
Any more questions? Okay. If there are no further questions, then I would like to thank, on behalf of SGTI committee, to Dr. Arora, and I will announce the next talk very soon for the next month. Dr. Bose, if you have anything to say.
No, it's fine. Thank you very much. We must appreciate and give a round of applause to Dr. Kusumita.
A round of applause, yes.
Thank you so much.
A virtual round of applause.
I'm very happy to be part of this, and hope to learn more from everybody as we go through the lectures of the month.
I will request you to join us every month so that
yes, I'll make the point.
Part of our group as well.
Yes, definitely.
Thank you very much.
Thank you. Thank you so much.
Thank you very much. Okay.
Okay.